Hello, Professor. My name is Gurmesh, and this is my assignment one. In question one, it gives us dimension of train images, train labels, test images, and test labels. In question two, it gives us length of train labels and length of test labels. Looking in question three, it gives us first 10 train labels, first 10 test labels. Question four and five, digital content and plot of train images. When we inspect train images, we see a 28x28 array of pixel values ranging from 0 to 255, representing the intensity of each pixel. Plotting this image really reveals a visual representation of the item. Question 6, label for index 5 in train label gives us a pullover. Now question 7 and 8, digital content and plot of test images. Similarly, test images 500 shows another 28 x28 array of pixel values. Plotting this image allows us to visualize a test item. This helps us understand the data our model will be evaluated on. Question 9, label for test images. If test label 500 is for example 2, this also corresponds to a pullover. Question 10, importing Keras model and layers. We import TensorFlow STF and Keras from TensorFlow. Keras provides the necessary models and layer module for constructing our neural network. Question 11, we define a neural network as Keras sequential model, which is a linear stack of layers. We named it my network. Question 12, the first layer we add is Keras.layers.flatten input shape. This layer transforms the 2D 28x28 pixel image into a 1D array of 984 pixels. This flattening is crucial because our dense layer expects a 1D input. In question 13, we normalize the pixel values of both train image and test image by dividing them by 255.0. Question 14 and 15, adding hidden layers. Now we add two dense, fully connected hidden layers to our network. The first hidden layer has 512 neuron and use the ReLU rectified linear unit activation function. The second hidden layer has 128 neurons, also using the ReLU activation function. Adding multiple hidden layers allows the network to learn more complex patterns and representation from data. Question 16, adding the output layer and softmax explanation. The final layer is a dense layer with 10 neurons corresponding to our 10 fashion categories. It uses the softmax activation function. Softmax is used in the output layer for multi-class classification problems. It takes a vector of arbitrary real valued scores, log tests, and transforms them into a probability distribution. Question 17, we have option A and option B, in which model A is complied with Adam optimizer, sparse categorical entropy loss, and accuracy metrics. Model B is compiled with RMS prop optimizer, categorical cross entropy loss, and accuracy metrics. Now, question 18, training with the fit command. We trained both models using the fit command for 10 epochs. An epoch is one complete pass through the entire training dataset. During training, the model adjusts its internal parameters, weight and basis, to minimize the loss function and improve accuracy. We observe the training process for both models, noting their accuracy and loss over each epoch. Question 19 and 12, comparing fashion MNIST with MNIST. MNIST is generally considered more challenging than the original dataset, while MNIST consists of simple handwritten digits. Fashion MNIST features more complex images of clothing items. The variation in style, texture, and pose make it harder for a model to distinguish between categories like a t-shirt and a shirt or a sneaker and an ankle boot. Question 12, interfering from accuracy, differences, and reasons. The differences in accuracy between the two models, option A and option B, are generally lower accuracy compared to a typical MNICT model can be attributed to several factors: data complexity, optimizer choice, hyperparameters, activation functions, model architecture. Now, question number 12: evaluating accuracy and loss and detecting overfitting. After training, we use the evaluate function to assess our models on the unseen test images. Model A, test loss 0.3613. Model B, test loss 0.4681. Comparing the test accuracy with the test accuracy for A and B helps us identify overfitting. If the training accuracy is significantly higher than the test accuracy and the training loss is much lower than the test loss, it indicates that the model has learned the training data too well, including its noise, and is not generally effective to new unseen data.